All right, check.
There we go. Continuing the presentation, we are continuing with the laser target mensuration module for small UAS aircraft. This is a brief outline of what we'll be discussing today for our senior Capstone project, and a quick introduction to our team. So I am the project leader, Jonathan Hogerheit, for those of you who haven't met me yet. Lucia is our software lead. Brian is our hardware lead, and Miguel is our mechanical lead, which for the purposes of this project was primarily CAD design and production of 3D printed parts. So the original motivation for this project comes from my background in the Marine Corps as an artillery officer. A situation that I heard described by a number of my peers who did combat tours in Afghanistan is you might see something like what's depicted here, a roadside bomb or an insurgent attack against a convoy, and you might have friendly forces that get pinned down by fire, explosion, what have you. You might find it very challenging to get an accurate enemy location that you can call in fire support onto that location and be able to close with the enemy or continue on with your movement. So existing solutions are either usually much too expensive or scarce resources or limited in capability. What we have depicted here on the bottom left, this entire system cost, I think it was about $300,000, including the launcher. And obviously with the launcher of that scale, it's not a very portable system. It's not very responsive or available. On the right, it's obviously a much more miniature and portable system. Still costs about $30,000, and it only has an optical sensor. So actually extracting target information is not possible with this platform.
So for the project description, we wanted to create a laser targeting system. We wanted to use our joystick to control the camera and the laser, have the RF communication communicate between a ground PI and a PI on the drone, and collect data from the drone, which would be displayed on the ground. For our system description, the person operates the joystick on the ground, which communicates with the RF to the RF on the PI. Basically allows the motor to move the camera and the laser, as well as collect data from the PI, send it back to the ground, and display it there. So, for the related theory, this is a military grid system. Basically, this is, you take the longitude and latitude, and we use an open source library to basically plot it on grid squares, basically on a map. This grid system is used by NATO. Basically, they overlap the tiles on a map, and each point on the tile has a longitude and latitude, and we just go based on that to find the point. So, in order to obtain the altitude, we use the pressure and the temperature in the above formula. We needed the altitude to calculate the horizontal distance, given that we have the laser distance, using the Pythagorean theorem. Also, the compass header angles are 90 degrees out of phase with the trig angles, and we use the formulas below to adjust that. For our hardware design, for the first iteration, we started off with a threading design to close the module. We wanted all our circuitry encapsulated in the module. And for the second iteration, we opted to switch for a teeth and lock mechanism because the threading wasn't working out so well. And for the final iteration, we added a ring and a hole in the bottom so that you could add a slip ring into the hole, and the tiny rings on the side would be able to attach to a vehicle. You put screws or nails in them.
So this is our ground box design. This is the first iteration of our ground box, and what we wanted our ground box to do was store all of the necessary components to process all the information that was coming from the drone module. We also outfitted it with an LED display so that we could easier display all the incoming data. So these are a couple of illustrations of the first and second iteration of our drone module, and you can see from the first to the second, we added a compass and a barometer, and an Arduino, so that, and we also better utilize our space on the board, so when we integrated the whole system, it would be easier to wire up. So for the ground module, we had a joystick so that the user could control the angle of the laser and the camera. And in order to send the joystick values, we used an analog transceiver so that the values could be sent to the drone module. So for our wireless communication, the first iteration of our code was only able to send joystick values, and it wasn't able to receive any values. So what we did to fix this problem is we opened a read pipe and closed the writing pipe at the end of our loop so that all of our values could be received. And for our calculation function, in reference to our related theory, this is where we implemented all of that. First, we calculated or generated an altitude value based on our barometer values of air temperature and pressure. And then from there we used the Pythagorean theorem based on our laser distance to calculate the horizontal distance to our target. And from there we took the x and y components of that horizontal distance to our target, and we converted that into a GPS coordinate, which could then be converted into a MGRS coordinate.
So for our first unit test, we used the wireless communication as it's one of the most important parts. So we sent a value over 100 times and just tested how long it took. On average, it was 182 microseconds with a high of 188 and a low of 180, so that it was very consistent. And then we wanted to integrate that with the joystick and moving the servos. So we were able to have an 83% accuracy of moving a servo with the joystick commands. And we have, it would move by itself sometimes, or it would be very delayed. And we believe it's because of noise interference in the room. And lastly is the acceptance test of the calculations, because if the calculations are wrong, then you're hitting the wrong target. So the GPS accuracy was rated for plus or minus 10 feet horizontally, and vertically plus or minus 100 feet. So 100 feet is a bit too much, so we used the barometer instead to calculate the altitude, which has a better rating of plus or minus 6 feet. So the laser had less than a foot of accuracy, so overall the radius is 11 feet accuracy. And for reference, the a causality radius of an artillery shell is about 164 feet, and for a 60 millimeter mortar is about 30 meters. So that means even though it might be 11 feet off, you'll still hit your target. So our team has successfully created a prototype that highlights the main functions of our project. We learned valuable skills like 3D printing design, Arduino and Raspberry Pi interfacing, and different communication ports like I2C, SPI, and UART. We still need to fix our power issue because the system itself is extremely power hungry. So that would be something we'd like to do in the future, as well as make our own PCB, overlay the calculations onto the video instead of having it on a separate screen, and we would like to weatherproof it for military purposes. So right here is a video of our demonstration. So for demonstration purposes, we're just showing the ground side, the drone side running. So this is the drone module laid out so you can see all the components. So if you look right there, there is a servo. If you wait a second, Ryan will move it with the joystick and you'll see it move. Unfortunately, it disconnected from the camera, but it does move by itself. Well, not by itself, but with Ryan's control. So here is a live video feed, which is attached with the laser, so it's coaxial, so you can see the target. And then this is the distance location. So the first two digits is the distance in meters, and then the rest is the location in grids.
So here's a list of
components that we ended up using for this project. As you can see, this is slide 1 out of 3. But we ended up using a video upscaler. Right now, we used a drone FPV transmission system that puts out an analog system. So this allowed us to upscale it to the HDMI signal that our LCD display for the user was able to see. Power supply, some other basic sensors, logic level shifters for our time of flight sensor,
We use two different radio frequency channels, one for servo control and one for video streaming. This allowed us to not have to worry about timing and latency for the video. It just had a dedicated pipeline, so it was very real-time display. We did have some interference from Wi-Fi, as mentioned, due to being on the same bandwidth as normal routers. Slip ring allowed us to communicate between the different segments of the module that we designed and the GPS sensor. A couple of components were already owned, which helped to reduce the actual out-of-pocket cost for this project. As you can see, we actually spent in the neighborhood of $400, maybe a little bit more for some small components like heat shrink and the like. Some of the standards that we tried to adhere to, IP65, we didn't quite get there in terms of ruggedizing or weatherproofing it. HDMI communication, GPS, we were able to parse NMEA sentences into GPS lat long into MGRS, which is our goal for military applications. Some of the ethics considerations that we put into designing this is the FAA is obviously trying to get on top of the explosion of drone use and application in the United States. That is somewhat mitigated by the fact that this would be applied in a combat zone, not in an urban environment primarily. However, there is some consideration for safety and so forth with our design product. In particular, with the laser that is mounted on the drone sensor pod, we would have to be concerned about if somebody would be misusing that to interfere with pilot vision or things like that. That kind of harassment wasn't distant as a problem. The last one was probably intellectual property. If we were to continue on with actually designing and implementing this on a commercial scale, we would either have to, our goal would be to adapt all of the modules that we bought off the shelf for this prototype into a singular PCB. We'd either have to get licensing rights for those circuits or design our own from scratch. So that would avoid the licensing issue. That's the long and short of our project for the Capstone. At this time, if you have any questions, we'd love to answer them.
That I want to make sure I understand. The information collection is done on the drone?
Correct.
And it goes down to the graphic?
Correct.
Okay.
So the collection and calculation. So really the receiver is just there to display the information to the user. The only information that the drone receives is from the user for the pan and tilt system on the camera and laser.
Would it be more beneficial to send raw information and then do calculations at the ground station?
So the challenge that we encountered was we were actually intending to use a Raspberry Pi Zero on the drone side because it's a $5 chip, it's very light, it would allow us to miniaturize even further, but basically it couldn't handle interfacing with multiple sensors. The processor at RAM got overloaded really quickly. So we ended up needing to upscale to a Raspberry Pi 3D Plus on the drone side, so we may as well just do all the calculations at once.
Also, for like bandwidth purposes, sending that much information was difficult, so it's easier just to send like a 12-digit or 12-character long instead of sending continuously sensor information. It would have overloaded the system. We tried it though.
That was our original plan. Any other questions? All right, thank you so much for your time.